This presentation is lucky.
Okay.
Goes up right away.
So, oh wow, that should say reduction. Okay, cool. Reduction of the 1,8-dimethoxy anthra-quinone. Okay, so that's what it starts out as. The one on the bottom left is what happens in the lab, is where the bottom oxygen gets reduced. And what doesn't happen is at the top oxygen gets reduced. And these are, it's a double bond and a double bond, and these are alternating doubles, but I don't know, DMD doesn't show those, so just imagine it. Yes, there's the bottom, top. Yeah. Okay, now we're looking at density of states for the original molecule, so unreduced. Here's the HOMO orbital, there's the LUMO, very small up there. And we'll compare the density of states in a minute. This is just to give you an idea of the orbitals. The HOMO orbitals here are on this guy and this guy. They're up here for the LUMO, and this is the bottom reduced oxygen. Then the top reduced HOMO is here. LUMO is in the same spot, but on a different orientation. Okay, so now comparing the density of states. The original and the bottom, the top reduced, look very similar on where the HOMO peak is, so it's like -4.5 pretty much. And then when it gets reduced on the bottom, it gets shifted to around -5. So that just shows that it reduces on bottom because it's a little bit easier on they're at a lower energy, which is better. Okay, now we're looking at absorbance. And I didn't really find anything meaningful from here. It's just kind of cool to look at, I guess. So here the peak is, the rightmost peak is like high 500s. Here it's like high middle 400s. So I don't know, nothing really interesting there, just looks neat. And then here we have like a heating simulation. So 100 femtoseconds. They all start at 500 degrees Kelvin, but it's kind of hard to see because it goes down and up so fast. So again, same configuration, the original molecule, reduced on bottom, reduced on top. And the only thing you can kind of see, maybe, is that when it's reduced on bottom, it seems to even out a little more, so that could suggest that it's more stable under heating, but I don't know, this might not actually be a trend. I should have run it for longer. And here we go again. See it move. This is the heating. And you'll see the important parts in detail in a minute. But it's just kind of fun to see it dance around. Okay, so again, this is just a simulation. It's not like we're actually observing what is happening. But it's just kind of neat. So when it's reduced on bottom, the bond just sort of wheels around without moving anywhere significant. But then on the top, the hydrogen is kind of all over the place. So I don't know if this is actually suggesting something, but it looks pretty cool. All right, so conclusions are when it's reduced on bottom, it is lower energy shown by the density of states. Temperature plots could be showing us something about like stability of the bottom reduced molecule, but I don't actually know if that's a trend. And the molecular dynamics are fun to look at, and it looks more stable when it's reduced on bottom.
Okay, let's thank